Okay. So number one, we've got, again, what creates the northern lights or the auroras? That is going to be solar wind. Solar wind, again, just like the Earth has an atmosphere, the sun has an atmosphere as well and has wind as well, but it's not near as pleasant or nice as the Earth's wind. It's supercharged and super hot. Secondly, what is the difference between a prominence and a flare? A prominence and a flare, guys. Well, if you can look down here, you can see these things coming off the surface of the sun. Okay, the ones that shoot out into space, those are flares. So they're both kind of explosions off the surface of the sun. The flare goes away and it just goes out into space, but the prominence is going to return to the surface like a rainbow. So a flare is like a fire explosion, goes out into space.
Students, please pardon this interruption at this time. Please release students to their math boot camp at this time. There was a pass in boxes for students who are supposed to be participating in that boot camp. Please release them at this time to that location. Thank you.
All right. Whereas the prominence is like a fire electric rainbow that rains back to the surface of the sun. And then lastly, maybe a little scary here, what happens if one of those flares goes right towards the Earth? Scary situation. Well, it's not as scary as you might think. Okay. The Earth has a magnetic shield around it. So that magnetic shield protects our planet from really getting much harm from the flare. But anything in space, well, that's going to be potentially very damaged. Okay. So satellites could get disrupted, and you're going to see potentially power outages, power and internet outages from this situation. Okay. Questions, comments on that? And then Angel, that's fine as long as you, just for the lesson, you can take it out later. Yeah, appreciate it. All right, let's go ahead. Let's move on to the table of contents. 4 to 5 is we talked about the outer layers of the sun. We talked about what happens on the surface. Now I want to get into what happens on the inside of the sun. Angel, did you happen to have the sheet? Did you need me to give you a copy? It's Thursday, you need a copy? Okay. So go ahead, get the table of contents situated. I'm going to give our in-person students a copy of the document that we saw Thursday. I'll show you. You did this half Thursday, or you did this half there? I'll show you that. All right, let's go ahead and move on then to our first practice question of the day. Again, you're going to answer your answer in the chat. We'll throw back from last week. And you can use your diagrams that you made from last week for these as well. Okay, so now what I want you guys to do is I want you to list the correct order of the outer sun layers, not from outside to inside, from inside out. So list the correct order of the outer layers from innermost outer layer to outermost. What's the correct order? Is it A, photo, chromo, corona, B, corona, chromo, photo, C, corona, photo, chromo, or D, chromo, photo, corona? What do you guys think? What do you guys think? Answers in the chat. One second. Gotta type my code in. Can answer in the chat for participation, guys. Great job. Appreciate you people. I'll preach all the answers. Got Michaela, thank you. Joseph, thank you. Sanaya, Irene, I need more people to answer. More people to answer. Get 10 seconds, 10 seconds. The correct order of the outer layers from inside out, inside out. 5 seconds. Again, if you do not answer, you're losing out participation. Okay. So the correct answer is actually going to be letter A. Photo is the innermost outer layer. Chromo, then the corona. So props, shout outs to Sanaya, Diego, and Michaela for getting the right answers. Congratulations. Great job, everybody. So yeah, got to know those orders from inside out or outside inside. Either way, either way. Okay, let's take a look at our first video questions of the day. You're going to write these just below your Go Blue. Okay, we talked about all about the outside of the sun, the surface of the sun. Now I want to know about the inside of the sun. I want to know, number one, write this question down below the Go Blue on page 4. I want to know, batteries run out of energy. Cars run out of energy. What keeps the sun alive? What keeps it around for so long, right? The sun, stars and the sun, just like everything else in the universe, it will run out of energy and it will cease to exist. Our star will either, and this is in a couple billion years, so we don't have to worry, but our sun, like all stars, will eventually run out and die, right? So our star will either explode in a supernova or it's going to just kind of fizzle out. One of the two will happen. Right? But what keeps it so powerful and around for such a long time? It's going to be around for approximately 4 billion years, maybe 5 billion more years. What is possibly keeping it around that long and keeping it sustained and alive? Hence, our source of life, right? The sun is what keeps our planet alive. Let's go ahead and check that out. And then number 2, now I want you to list the inner layers from inside out. Now list the inner layers from inside out. So I can take a great guess as to what the most inner layer of the sun's going to be. What do we call the Angel? What do we call the very center of something? The core, right? So for number 2, we'll say core, and then there'll be 2 more in the order that is shown in the video. Let's go ahead and check it out. Again, we're looking at the internal layers of the sun. Internal layers of the sun.
And
got a annoying ad. One second. Let me wait for the ad to run out. Never been a fan of these advertisements. All right, 1 second. Let's check it out. Again, what powers the sun, keeps it alive, and what is the order of the internal layers from inside out?
gigantic nuclear factory, 190. Deep inside of the sun is the innermost layer, the core, which is a gigantic nuclear factory 195,000 miles thick. That's the equivalent of driving from New York to Los Angeles 70 times. In this most mysterious layer, the crushing pressure feels 150 times stronger than being deep underwater. Pressure and density are so great in the core that hydrogen atoms smash into each other, combining to form helium. Now atoms become highly unstable and release nuclear energy to become stable once again. We call this process nuclear fusion, and it's the very process that keeps the sun and all stars alive. Every single bit of energy that leaves the sun and reaches Earth originated from the core. The core is the sun's hottest layer. How hot? 27 million degrees Fahrenheit. That's hot enough to instantly melt lead, iron, brass, or any other metal. Just above the core lies the radiative zone. Now, the nuclear energy generated in the sun's core travels through the radiative zone in the form of electromagnetic radiation, better known as light. Density slightly decreases, but is still tremendous. The radiative zone is 186,000 miles across. And ironically, this is how far light can travel in 1 second. However, the radiative zone is still so dense that photons of light bounce around like a pinball machine. In fact, light takes around 100,000 years just to make its way through the radiative zone of the sun. Finally, we reach the convection zone, which spans for around 124,000 miles. Now density finally becomes low enough for light traveling out of the core to transform into heat. And just like this layer's name, the process of convection kicks in. Simply put, convection means hotter materials will rise, cooler materials sink. And as the heat from the bottom of the convection zone rises, it gradually cools, sinking back down again. This continual process happens in gigantic bubbles known as convection cells. Convection is also the same process that causes the big bubbles in a boiling pot of water. Well, there you have it.
All
Now you know a
right,
little
so
bit about.
great breakdown of our different internal layers. For number one, Angel, what did you have for what keeps the sun alive? Perfect. Again, that's a super important phrase, guys. Nuclear fusion, nuclear fusion. The fusion of atoms is what's keeping the sun so stable and so strong over such a long period of time. You're going to see that on your notebook check and your online test. Number two, did you also have the internal layers from inside to outside? Perfect, perfect. So we have the core in the middle. It can be radiation or radiative. Either one's fine. So I always say CRC. So if I know core is the middle, then I know the convective is always in the outermost part. So core, radiative, and convection zone. Core, radiative, and convection zone. Okay. Any questions, concerns on that? We're going to break those down here in a little bit. Okay. If you guys recall, let me go and show this to you on the, go ahead, Angel, if you could label the inner layers with the arrows that you see on the screen. For my online students, I'm going to go ahead and show you guys what I can see here. Okay. So if you look here, if you guys remember, I posted this in the chat. Layers of the sun, right? So what I want you guys to do is when you draw this in your books, because I'm probably going to use this for a notebook check, to be honest. This is a really important page. Remember, this is page three of your notebooks. Okay. We did the corona, the chromosphere, and the photosphere already. So today we're going to finish up core, radiation zone, and convection zone. Now, in the middle, as you can see through mine, in the middle, just write nuclear fusion, right there where the core is at. Nuclear fusion. In the second layer, you're going to write, just have some squiggly arrows that go straight out. Squiggly arrows that go straight out. And then in the convective zone, that outermost inner layer right there, I want you to draw arrows that kind of go like in a circular motion, circular arrows. So we go from convection, circular arrows. Radiative is going to be linear, squiggly arrows. And then nuclear fusion in the middle there, in the middle. I posted it last time. Let me go ahead and try and posting it again in the chat. Because now I'm getting this figured out, am I right? Okay. And we're going to move on and talk about core right away, as soon as our in-person students are ready. And again, this will be on YouTube later, no worries. Let's see. 1 second, everybody. I'm just trying to find. See if I can find it or not. It might take a while if I do it this way. All right, one moment, guys. I'm just trying to post the document again. Otherwise, I think we're pretty much okay. No one's asking for it for me, but let me see if I can find it. If not, we'll just move on. Because last time I put it on the desktop, and I could just get it really easily, but I cleared out the desktop recently too, so probably why it's not popping up. Well, you guys get the idea. So again, we should have drawn this already. I've posted it already. If not, pause the video. Make sure you draw this in notebook page 3. Okay, so let's get into the first box. So the box on the top right of the sheet where it says core. I'm going to give it to you right away. And we'll walk through each one. Let's see. Okay, so let me find what I need here. Okay, so we can now see we have the core on the top right, of our sheet, our notes there. Oh, my best, get that. Okay, Make sure to have all of that written down. Let me make sure you guys can all see that. Okay, give our in-person students a moment. We're now at the core, That's on the top right of the sheet we just made, or the sheet you guys have already made on page 3. Okay, obviously it's the core, it's the center of the sun. And we know the corona is the hottest outer layer, but as you guys probably already knew, the core is going to be the hottest of all the layers. Super, super hot, tons of pressure, particles moving at high speeds, faster speeds than in the entire solar system, right? Now, some key things to also note. Again, make sure to write all this down. We always got to know nuclear fusion. That's an obvious one, right? We got to know that's what powers it. But I need you to also know the elements that are inside of that fusion, okay? Usually they consist of fusing hydrogen, element with atomic number 1, hydrogen, and think of the sun like a balloon. What makes a balloon larger? It's helium, right? So hydrogen plus helium are going to combine and power the sun for billions of years at this point. Crazy stuff, really cool. I'm going to show you like a 1-minute video clip that kind of walks you through that. All right, and it's where we have the most energy, the most light, and radiation. Okay, so the energy eventually it's gonna combine and fuse, and then be pushed out to the next layer, which we'll talk about here in a moment. Okay, all good, Angel? Okay, so let's go ahead and check out. I'm gonna play just the first minute and a half of this video. How does that process look, and how does that work? This is a good kind of example here. Now, believe it or not, guys, scientists are trying to come up with a way to make mini stars and actually put them in labs so that we can harness energy from them. But this is super difficult and could be dangerous if there's like a black hole created, because black holes come from stars, guys. So we don't want a black hole like devouring our planet, right? Something to maybe be worried about. Let's check out the details on how nuclear fusion works inside of the sun.
The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever.
Okay, so some neat stuff there, but again, the idea is the sun, it's massive, it's got tons of heat, tons of pressure, and particles moving at super high speeds that connect because of that pressure. That gives it a ton of energy. Cool stuff there. Let's move on now to the radiative zone. And again, we're not in person, so we're not going to worry about this. But let's go ahead and make sure you got all that for the radiative zone, guys. Basically, this is like the middle point of where the light and energy is traveling. Okay. Think of the radiative zone like the oven. Okay. You ever seen like a hot summer day, how you see like the air right above the pavement's kind of wavy? You ever seen that before, Angel? It's kind of wavy. Well, we call that radiation. So when you open the oven, heat is just hitting you like in a linear way. It's hitting you straight on. So you guys can see this here. It's kind of like a squiggly line. It just heat moves in waves, right? So that's the idea. Radiation, heat moves in waves. It's going to be steady and stable like an oven heating head on, maybe like a Thanksgiving turkey or baking a cake. Okay. So once heat travels through those lines, it's then going to start to change a bit. It's going to switch up a little bit, right? And our last one's really short, guys. It's going to switch up in the convective zone. Again, feel free to take pictures if I'm going too fast. In the convective zone, it's now going to start to get a little crazy. It's going to start to the heat and the energy is going to bounce up and down. And this is what causes the sun's surface to be so it can be really unstable. So when you get solar flares, when you get solar prominences, you get all that stuff just flaring off the surface. That's caused by what we call the convective zone. So now we go from an oven and now we're inside of a microwave. When you're in a microwave, the heat's just bouncing all around. Like it's just bouncing all around the microwave. Same thing happens with the sun's heat here. Okay. Super important. This instability is what creates the sun's magnetic field, Okay. That's on the bottom right of your notes there on page 3. All right, guys, let's go ahead and do our last question of the day.